pumping lemma for regular languages, what we have to do is we use this pumping lemma to prove that a language is not regular. Basically, when we want to say a language can be finite language or infinite language. A language L accepted by finite automata, then it is a regular language. If we want to if we find a pattern, for example, let L equals to a power n is greater than or equal to 0. Pattern here we are finding is L equals to a power 0, a power 1, a power 2. The difference over here you see is 1, 1, 1. Now next one, if you see L equals to a power n, where n is an even number. So here you can see n equals to 0, 2, 4 and like that. So here you will see a same equal difference between all the parts. Now if you take another example, L equals to a power p such that p is a prime. Now p equals to the prime numbers we have to take 3, 5, 7, 11, 13. Now if you see here, the difference between 3 and 5 is 2. And between 5 and 7 is 2. 7 and 11 is 4. 11 and 13 is 2. Again, if you see 17 and 23, the difference is 6. So there is no proper pattern here. So if we want to divide the pumping lemma, if we want to find, if we are able to find a pattern, then it is a regular language. So if we are not able to find a pattern, then it is not regular language. So we can say now this is not regular. Why? Because we are not finding a pattern which can be regular pattern. So now if you take W equals to XYZ, where mod of XY, that is the length of XY, the string XY, is less than or equal to M, and Wi is equals to x y power I z. That means if there is a path from this point here, you can take this as an epsilon, then there is a path x, and then y can have a number of times looping, and it is then going to z. So y can be pumped. So we can have W equals to x y power I z. This is again pumping lemma has been proved. This is already covered in the class, but once again I have recorded this. So if you have any doubts, you can ask me later.